I'm now going to talk about parameter learning for undirected tree-structured graphical models. And the basic idea is that assuming that we know what the tree is, so we know what the nodes and edges are, we want to figure out what all the potential tables are for this graphical model. And we've actually already seen an example of this when we looked at naive Bayes, where we had this particular graphical model, and we assumed we had access to training data. Okay, so the ith training data point consisted of a label, C, so either spam or ham, and a bunch of features y1 up through yj. Each of these was either 0 or 1 for whether the jth word in a dictionary appeared or not. Okay, and we had I going from 1 up to n, so there are n training data points. And the high-level idea was that for this graphical model, we want to learn for the random variable C, the table PC, where we have spam and ham. Here the probability table entries were S and 1 minus S. Okay, so C. And for each of these edges, we were also trying to learn a table. So in particular for the jth edge right here, the table we were trying to learn was P of yj given C, where C is either spam or ham. Okay, and we have yj here 0 and 1, and for spam this is qj, so this is 1 minus qj, and for ham we had pj and 1 minus pj. Okay, and note that here this thing is a distribution and each row here is a distribution. So what we were trying to do was learn, well, there are capital J edges here, and so 2 times capital J plus this one different distributions that we were trying to learn, parameterized by the S, the PJs, and the QJs. Alright? And how that appeared in the formulas was that we had the log likelihood across our training data, which we then wrote in the factorization for each of the training data points, where we have the class and then the features given the class. And then what we showed was that we can break up the log likelihood into 3 pieces. Okay? There is a piece that only depended on, even though we wrote parameter theta, this piece actually only depended on S. Okay, so this is just S here. This piece here, instead of depending on all of theta, this only depended on Pj, and this piece here actually only depended on Qj. And in particular, you can view this as this thing here corresponds to the log likelihood for random variable C. This piece here corresponds to the log likelihood of random variable yj given C equals ham, and this piece is yj given C equals spam. Okay, and of course we're summing over the j's. So what we're saying is that the log likelihood of all the training data decouples into the log likelihood of 2j plus 1 different finite random variables. Okay? So maximizing the log likelihood is the same thing as maximizing the log likelihood for each of 2j plus 1 finite random variables. And as we've seen now, we know what the answer is for the maximum likelihood estimate for any finite random variable. We just look at the empirical distribution. And so, for example, that's how we ended up with S being the fraction of training emails with label spam. Okay? Now let's look at the more general case of undirected trees, where we begin with this tree we've seen before. So in the general setup, we would have a tree like this, and we have training data. Again, the ith training data point consists of observed values for all the random variables in the graphical model, so x1 up through x5 in this case, and we're going to assume once again that we have I going from 1 up to n. Okay, so here we're going to choose arbitrarily a root for this tree where we're just going to pick x1, and so by doing that, it means that we're going to learn the following tables. We're going to learn the probability table for px1, so this is going to have a number of entries, and then for each of these edges, so for example for this edge, we're going to learn the probability table for x5 given x2. Okay, so x2 indexing the rows and x5 indexing these columns. And so as with the naive Bayes case, only for what we choose to be the root do we learn a probability table that corresponds to a one-dimensional table. So this is one distribution. And then for each of the edge potentials, the table we're learning is this conditional probability table where each of these rows is going to be a distribution. And so what's going to happen is that when we look at the log likelihood across all of the training data, as before, we're going to incorporate the structure. Here I'm being lazy and not writing the subscript with all the random variables or the parameters, simply because if I did write those in, this would look like a complete mess. And just to be a little bit informal here, I'm not writing all of that stuff out. But the log likelihood, once again, incorporating the structure here, we have this factorization where we have chosen x1 to be the root. And so, as before, this log likelihood is going to break up into several sums here. Okay? And again, I'm being sloppy and not writing in all the parameters, which I'll do so now. But the point is that this is going to decouple into this thing is the log likelihood for random variable x1. This thing is for x2 given x1. This thing is for x3 given x1. And then x4 given x2. x5 given x2. And the parameters now I'm going to be calling the following. So I'm going to call the parameters of this table for this root node theta of 1, where I'm going to say theta of 1 semicolon a is going to be defined by I look at the 8th entry. So this is the probability table of x1 evaluated at a. Okay, and so here I'm going to introduce notation where for the conditional probability table here I have theta 5 given 2 will be the parameters for this entire table, where theta 5 given 2 of semicolon a given b is going to refer to the probability table of x5 given x2 of a given b. And so what we're trying to do here is, of course, learn all of these thetas. And for this x1, the parameters for this table are theta 1. Here it's going to be theta 2 given 1. Again, up here I was just giving an example for theta 5 given 2, but of course we have theta 2 given 1, 3 given 1, 4 given 2, and 5 given 2. So theta 3 given 1, theta 4 given 2, and theta 5 given 2. Okay, and as a reminder, this piece, for example, can be written as sum over all possible a that x2 can take on, and we're going to sum over all the training data for the indicator value for x2 of I being equal to a times log, so this whole thing, times log of p x4 of I given a. Alright, I'm writing this just to say that for each of these terms corresponding to a conditional probability, we can break it up into the cases for what we are conditioning on. Kind of like how in the naive Bayes case, we broke it up in terms of ham and spam, which is what the different classes are. In general, we can, for each of the things we're conditioning on, we can break up this summation into a summation where we specifically look at each possible value of the random variable we're conditioning on. That makes it clear that here, this overall log likelihood, when we try to maximize it, it is the same as maximizing a bunch of log likelihoods. And for each of these terms corresponding to a conditional probability table, it actually breaks up into multiple finite random variables that we're learning the parameters for. So this thing here corresponds to random variable x4, condition on x2 being specifically equal to this little a. And of course, the parameter for this corresponds to the part of theta 4 given 2, where we're conditioning on x2 being equal to a. Alright? So finally, we recognize that to maximize this log likelihood is the same thing as separately maximizing each of these log likelihoods, where again, for each of these conditional probability tables, we would break it up into something like this, and maximize for each of the finite random variables involved. And the end result, of course, though, is that theta 1 hat of a, again, theta 1 of a is the probability table for x1 evaluated at a. Theta hat of 1 of a, the ML estimate, is of course going to be the empirical distribution for x1 evaluated at a, which is the fraction of times in our training data that we see x1 being equal to a. So that's going to be the ML estimate for theta 1, and then for each of these conditional probability tables, we're going to have theta hat of I given j of a given b here is going to be equal to the empirical conditional probability distribution of xi given xj of a given b, which is going to be equal to the fraction of times amongst when we see xj equal to b that xi is equal to a. So that's going to be the sum from, I'm now going to use dummy variable L for the training data, so L going from 1 to n of indicator that xi of L is equal to a and xj of L is equal to b, all divided by, and then I'm going to sum up over all the training data where we have xj of L is equal to b. Alright? So these are the ML estimates for all the parameters in these tables. Okay? And so let's recap what's happening in the general case. For parameter learning and underdirected trees, what we did was for a given tree, we arbitrarily chose a root, for example, x1, and once we choose a root, that's going to give us a specific factorization, right? It's going to say, okay, probability of x1, and then x2 given x1, x3 given x1, x4 given x2, x5 given x2. If we had, for example, chosen x2 to be the root, then the factorization would be different. You would say p of x2, and then p of x4 given 2, 5 given 2, 1 given 2, and then 3 given 1. And you would learn a different set of tables, but that's okay. You'll get a different way to parameterize this graphical model. Once we've chosen a root, so in this case x1, and we have the factorization, that makes it very clear what the tables are that we're trying to learn. And also, given the training data, we can then just use these two equations to completely populate what all the ML estimate entries should be for these tables. And that's it. We reduce the problem for parameter learning for trees to the case of parameter learning of a whole bunch of finite random variables.